Good afternoon, everyone, and welcome to Meteorology. Welcome to all of you who are tuned in online as well. Thank you for joining in. And I don't know, is there a way for them online to ask questions? Okay, email, okay. As long as that's been sorted out. I'm Augustine Icapelli, and welcome to the class. We're going to have, as you know, 4 sessions throughout the month here, every Tuesday afternoon from 1 to 3 p.m. And today we're going to go over, actually, I'm going to move ahead here a screen. Well, I'm jumping ahead of myself. I got to do the housekeeping first. Okay, housekeeping. For those of you who came in kind of through that main entrance here today, the restrooms are kind of back out that entrance, and there's a set kind of down this end and down that end. Feel free to get up and use them at any time. You're not going to upset me or anything like that. And comfort is what we are looking for here. Our class periods, like I said, we're going to be running about 2 hours, give or take. In this sort of environment, it's a little different for me than when I've taught this class before. So we'll see where our time kind of works out, but it should be about 50-minute segment, 10-minute break, and another 50-minute segment, leaving a little bit of time here and there for questions as you may have them. Feel free, though, to ask questions at any time. You can come up to the mic up here. Otherwise, if you're shouting it loud enough, I will try to repeat the question over the microphone for our guests watching online. A little bit about me. Actually, I noticed on this while I was reading back through this right before the class, and I'm slightly out of date here, and I'll cover that in just a second. I have a bachelor's in science in meteorology from Valparaiso University. Graduated in the year 2000, which dates me just a little bit. Worked here in Wichita for a company called Weather Data Incorporated. They're now known as AccuWeather Enterprise Solutions. When I worked for them, they were in the Farm Credit Bank building. They've since moved into the Bank of America building and are in a much, much bigger place than when I worked there. I was there for a couple of years and decided that I wanted to go back to school and get a master's in business and kind of go from there. So I still have a lot of love for meteorology in my heart. And this is getting to teach this class is a way for me to kind of keep my finger on the weather a little bit. I've been married for, 19 years now. And I have 2 boys and 1 little girl now. A little 4-month-old. So, and the kids are now almost, 11 and 3, the other 2. My day job with the university is I'm the director of the WSU West campus location. If you've never been out west, it's right near it's across the street from the Menards over there at 37th Street and Mays. And, I've been teaching my meteorology class, my 16-week, if you really like this, the 16-week class is out there as well. I've been teaching that for a long time, it feels like now, since about 2006. And then finally, if that isn't enough stuff on my schedule, my wife and I own Augustino Brewing Company on the west side of town, and they have been running that for getting close to 3 years now. So we do a lot of things. So looking at what we're going to do over the course of the next 4 weeks. Today is, for those of you who are kind of history buffs, you're going to love today. It's a lot about the basics and the history of meteorology. So we're going to kind of go from the very early study of the science of meteorology up till today. And you'll see that, we've certainly come a long way over the last, about 2,500 years. The science of meteorology relative to some other natural sciences is very young in terms of the sophistication and the science behind it that we have today. Next week, we will move on to talking about severe weather and also forecasting. We'll get a little bit of a look into what I did day to day when I was a meteorologist and kind of what meteorologists tend to do in general. Then the day 3 is winter storm forecasting. It's actually going to be a split day. Half of it will be discussing different types of winter weather and forecasting winter weather. And the front half of that day is going to be looking at the storm that sunk the Edmund Fitzgerald in November of 1975, which is also kind of a discussion of mid-latitude bomb cyclones. So, and then finally, we're going to wrap up with climatology and climate forecasting and get into a little bit of the science of that, and maybe even touch on a little bit of the controversy around climate and climate forecasting, try to clear some of the mud out of the way. So let's just start with a little bit of history. Science of meteorology goes back really to the dawn of man, but in terms of really developing some of what the foundation of meteorology is, started really in the early BCs. Around 350 BC is when Aristotle, who's kind of looked at as the father of modern meteorology, started describing the hydrologic cycle. And the hydrologic cycle is sort of how the water moves through our atmosphere. Basically, it rains from the clouds. The rain goes into rivers, lakes, oceans, and then eventually evaporates back up, becomes clouds again, and the cycle continues. And really, it was Aristotle that kind of got that whole thing started in terms of what we look at as the science of meteorology. As we got into the early AD years, our understanding of meteorology starts to increase a little bit. We build upon that foundation of Aristotle, but you've got to go over 1,000 years till we start to get into some of our increased knowledge in terms of meteorology. So we've got this, and I'm going to butcher the name, so I just kind of jump over it and you can kind of look at the letters too. But anyway, we start mathematically understanding how our eyes are able to take in light from the sun, from whatever, and we, are able to, by understanding the concepts of refraction and reflection, we're able to start understanding what the depth and size of our atmosphere actually is. Basically, what we know is that as light from the sun comes into our atmosphere, it's refracted. So we've got, light that is pure white comes into the atmosphere. Certain wavelengths of color start refracting out, and that's how we have a blue sky. And so we understood the depth of our atmosphere more in the early 1000s AD. Go ahead another few hundred years, and we've got St. Albert the Great. He proposes how our rainbows form through refraction through rain droplets. And this is kind of a graphic that goes into a little bit how we are able to view these rainbows. Basically, if you're trying to find a rainbow on a rainy day when the sun's out, make sure the sun's behind you. The sun's going to go past you, go into those raindrops and start refracting the sunlight through. And what you see here is that it's bouncing off literally the sides of the inside of the rain droplet and then back out toward you. And as it does that, it's refracting out the sunlight and bending it out into its individual colors. Now, depending on how many times it bounces through those raindrops, and this gets in a whole other area of geometry and things like that in terms of droplet size, it can actually bounce multiple times, and that's how you wind up getting secondary rainbows. So you'll see the first rainbow look normal, and then the second rainbow will be reversed above it. And in very rare cases, you can actually get a tertiary rainbow as well, but they are very rare. So we advance a little bit further into the 1400s now. And Korean prince starts to standardize our rain gauge. And just like anything in terms of measurement, it naturally winds up being associated with taxation. The invention of the rain gauge was so that the government could determine how much they could tax the farmers for their crops based upon how much rain fell during a season. So even at the onset of our understanding of meteorology, some of those advances were done for the taxation of the public. So more rain, more taxes; less rain, less taxes. So that was in 1441. Now we're starting to get into some momentum, because now we've got something that we can measure with for our start taking meteorological measurements. 1450. We start being able to measure the relative wind speeds. And this is done through the invention of the swinging plate anemometer. Now, most of you, if you've seen an anemometer for measuring wind speed, usually these days what you'll see is something that's got 3 cups on it and just kind of spins around. Swinging plate anemometer is just literally what it sounds like. It's a little plate up and down that, as the wind blows against it, it pushes it up, and depending on how far it pushes it up, it measures your wind speed relatively that way. Moving forward to 1643. So now we've got our rain gauge. We've had that for a while, but now we have the invention of a barometer, a mercury barometer, invented by Evangelista Torselli. You would think, being Italian, I would be able to pronounce that better. But anyway, so what the barometer does is it measures the changes relatively in the atmospheric pressure. So as the atmosphere gets heavier, as the pressure gets higher on the surface, it's pushing down that mercury. And as it pushes the mercury down, it's pushing it up the tube. And so if you measure the graduations on the tube, you can measure the changes in the air pressure. We had known as we took some of these measurements in this time that generally if the pressure was going down, it would wind up leading to rain and storms and that sort of thing. Whereas if the pressure was high, usually the weather was clear and nice. And so by measuring, by starting to take these pressure measurements, we were able to get a better feel for when the weather was going to change by seeing how the column of mercury changed with time. And then along those lines, if you hear of discussions of inches and millibars of mercury, you've got your average here is, the average sea level pressure is 29.92 inches of mercury, which is most meteorologists behind the scenes will use millibars. It's 1013.25 millibars. That's the average at sea level. We'll get into this a little bit more, but when we measure pressure, we're always measuring it and then converting it to sea level. And there's reasons for that from a meteorological standpoint, and we'll talk about that next week. But when we measure the pressure that we're measuring here in Wichita, Kansas, isn't really the sea level pressure until we convert it to sea level based upon our elevation, which I just basically covered on this. So your pressure, your actual pressure, is the pressure measured at a specific location, but by going back and knowing how high you are above sea level, you can convert that down because the pressure changes by about 10 millibars every 1,000 feet. And Wichita, for those of you who don't know, is about 1,299 feet above sea level. And so we have to do a little bit of conversion to get back down to the true sea level pressure, so that when you're comparing what the pressure is in Wichita, Kansas to the pressure in, say, Biloxi, Mississippi, you can compare apples to apples when you do that conversion. Otherwise, the natural pressure here in Wichita, Kansas is always going to be lower than it is in, say, Mississippi, Death Valley, any of those places that are much lower. Similarly, though, if you get in a car and you drive to, say, Denver, Colorado, the pressure is much lower in Denver than it is here. And the reason for that is because you've gone a little bit higher into the atmosphere. You're a little bit further above some of the oxygen, and so you've got less of that weighing down on you. So the actual pressure in Denver, Colorado, is much lower than it is here in Wichita, Kansas, as well. And because of that, if you're like me, you head to Denver, and you're kind of like, you feel maybe a little lightheaded, a little short on oxygen for a little while, until your body kind of recovers and gets used to that pressure change. Because Denver is more like, I can't remember, like 5,400 feet above sea level. So it's another 4,000 ish foot pressure change. So it's all relative, as they say, and that's true with pressure as well. So as we move ahead in terms of our development of our instrumentation, we get to Sir Christopher Wren, and he invents the concept of the tipping bucket rain gauge. Now, the first rain gauge that was developed was a rain gauge like what you might have in your backyard garden, just basically a funnel going into just a column that collects the water into it. So it just kind of goes 1 inch, 2 inch, 3 inch, 4 inch, and you look at it, you eyeball it. Okay, 1.5 inches of rain fell overnight. A tipping bucket rain gauge, however, is a device that, now the modern ones, in 1662, it was not an electronic version of this, but today they're electronically driven, and as about 1/100th or 1/10 of an inch, depending on the gauge, of rain falls, the tiny little bucket in there dumps it out and sets it back to refill. And so in modern days, each time it dumps, it sends that electrical signal to a digital readout that says, okay, we've got another 1/10 of an inch of rain or whatever. So in 1662 was the first development of this idea that we could, at that time, mechanically measure rainfall over time. Whoop, there we go. Now we start getting into a couple of at least last names that probably sound a little bit familiar. We've got 1714, Gabriel Fahrenheit creates the first reliable scale for measuring temperature. And he does this using a mercury thermometer. Bulb at the bottom, you've all seen these. As that bulb heats up, the mercury starts traveling up this graduated cylinder, and depending on how high up the cylinder it gets, it measures what the temperature is at that time. A little bit later, Anders Celsius proposes the centigrade temperature scale, which is also known today as Celsius. And that one is used by meteorologists worldwide, use Celsius typically over Fahrenheit. Here in the US, we're kind of the outliers, like we are in most of those type of measurement scales. But even once on our weather maps, once you get above the surface level, it's all in Celsius. At the ground level, if you look at a ground level weather map here in the US, which we'll look at next week, you will see that it is actually Fahrenheit that we use at the surface level, but globally it's all Celsius above the surface. In 1783, Horace Benedict de Saussure invented the first whalebone hygrometer for measuring humidity. Now, hygrometer is used for measuring, well, like I said, humidity. It basically is a measurement of how much water vapor is in the air. And the reason why that's important is, generally speaking, and you've probably seen this in your weather forecasts that you've watched on TV, the more liquid there is in the air, generally the higher likelihood we're going to wind up in the near future getting rain. Just having really high humidity is not going to make it rain or storm, but it is one element that we need, because no water in the atmosphere, no clouds, no precipitation. And so that's why this grabbing along with the rain, along with the temperature, along with the barometer, we want the hygrometer. We want to know what the atmospheric humidity is at a particular time. And those are really the four main things that we like to plot on weather maps even today. So moving ahead, 1803, so we're starting to get closer to modern time. We start deciding that we need to classify the different types of clouds we have in the atmosphere. And so Luke Howard comes up with our first scale, and this is the scale that's still used today for defining our clouds. And it's done by where the clouds are in the atmosphere. Our high clouds are our cirro clouds. So those are the wispy clouds you see going across the sky. Our alto clouds are our middle clouds. So you'll hear alto cirrus, alto stratus. That alto prefix is saying where it is in the atmosphere. And then you've got the stratus clouds. Those are our low clouds. You see a lot of those during the winter months when we have considerably less atmospheric forcing to make thunderstorms. And then that leaves the last category of clouds, which is our nimbus clouds, cumuloclouds. And those are the clouds that go vertically. And cumulonimbus, it means it's growing vertical. The nimbus is the rain, cumulo rain. So that scale is, like I said, used still today. Okay, yeah, doing okay. I've been kind of going a little fast through the early periods. I want to take a moment to see if anybody has any questions before we continue to push forward. I got a little bit of time. Anything? Okay. Yep. The question was, related to barometric pressure. And the student asked, why is it that we feel bad when the pressure is low, or just kind of different? That varies from person to person. I mean, some of it, I don't really have a great answer for you on that piece. There is medical research that gets done in terms of meteorology. It's not an area I'm real good at, but I feel like as I've gotten a little bit older, I kind of, when crappy weather is coming in, I'm just kind of feeling a little off myself. But it does get a little bit out of my expertise exactly why that winds up occurring. It could be a combination of things. As the atmosphere, as the pressure changes, it does, have an impact on what, how much available, oxygen's in the air, because as it gets compressed, breathing can become an issue. There's everything from, as the pressure changes or the winds change even, are you bringing more pollutants into your atmosphere locally? As a going down that road, as an aside, where general question thrown out, where is the most, for most people, when are you being exposed to the most air pollutants over the course of the day? Morning and evening, but where? For most people, your greatest amount of atmospheric pollution that you'll be taking in is in your own house, typically. When you're outside, because you've got the winds circulating around, it actually mixes a lot of the pollutants out. Our atmosphere naturally likes to correct itself. And so the atmosphere, and we'll talk about this later on in the class as well, the atmosphere always wants to get itself back to normal, nice, even atmosphere. And so our weather systems that come through are part of trying to mix the atmosphere back into stability. So kind of went off on a tangent there, but yeah. Other question? Yeah. Mm-hmm. Why it's 1013? I think it's just because it sort of is. The inches scale was developed. The inches of mercury was developed before the millibar scale was developed. But yeah, I mean, especially when you look at Fahrenheit, came up with his scale that kind of placed freezing at 32 degrees, boiling at 212 at sea level. And then Celsius comes along and creates a much simpler scale that goes from 0 to 100 for freezing to boiling. You would think that it would be a lot simpler like that for atmospheric pressure as well. But I'll be honest, I'm not, that's a good question. I'm not exactly sure why it doesn't just decide to go from 0 to 1,000, with 1,000 being your average atmospheric pressure. My only guess at that would be that when that millibar scale was created, that they didn't necessarily have a determination of what was true sea level pressure. But again, that for me, these are great questions. I'm actually not 100% sure why that would be. So, yes. The question, and I'm sorry for those of you watching that I didn't repeat the last question, but the latest question was there some jealousy between Fahrenheit and Celsius, that Fahrenheit comes out with his scale, Celsius comes out with his scale? My best guess on that one is it's just like today in research. If I come out with a research paper that says X, another researcher looking for something to research might take a little bit of what I had come out with and blended it with some of what they came out with to try to create something better. And so, is there an advantage of using one scale over another? With Celsius, the biggest advantage is the simplicity of the scale versus Fahrenheit. It's easy to remember the freezing point of water versus the boiling point of water. Shifting gears to Fahrenheit for a moment, because Celsius is based on water. Fahrenheit's actually based on the freezing point of alcohol. And so different temperature scales help with different things. There are other temperature scales that have been developed as well, some which are not used today, others that that we use in the scientific community. But Fahrenheit versus Celsius, as an American, I still think more in Fahrenheit, but yeah, the rest of the world thinks in Celsius, which again is probably the easier way to look at it in general, because you can generally think, okay, freezing, it's going to be snowing at 0 Celsius, 10 Celsius is kind of cool, 20 Celsius is feeling nice, 30 Celsius is getting kind of hot. And so it's I can see why the rest of the world kind of looks at us here in the US and kind of laughs at us, why we think Fahrenheit is so much easier than Celsius in terms of, understanding. But, if it's what you're used to, it's what you're used to. So, but I would say personally, going from Fahrenheit to Celsius, Celsius is definitely the more sensible in my mind for general use of a temperature scale. But I still operate in Fahrenheit too. So, any other questions? Okay. So we're in the 1800s now. Francis Beaufort, we were going back to wind speed. He invents what's called the Beaufort scale, because we like naming stuff after ourselves. And it's a scale for classifying wind speeds based upon looking outside and seeing how things are blowing around. So it's a scale that goes from nothing up to hurricane force scale winds. Moving forward to the mid 1800s, the Smithsonian Institute begins to establish a weather observation network across the United States. Now, here's what's really key about that. We think in terms of the fact that we have just always had universal observations of what's going on at a specific point in time across the whole earth, in terms of the weather. That's not true. Most of our history of understanding of atmospheric conditions and the weather in general at any point of time is through a lot of inference and a lot of trying to take observations through ice cores or everything from ice cores to cut sections of trees to looking at geological references. That's how we've, for the majority of human history, figured out what the climate was, what temperatures were over time. It's really within the last couple hundred years that we started getting to a point where we are today of, at any given point in time, we know pretty well what's going on weather-wise across the entire planet. And we'll continue forward to really realizing that our ability to know what really is going on at any given point across the entire planet at the same time is very, very young, probably within everybody in this room's lifetime, including mine. And we'll get into that, well, except for maybe a couple of guys working the camera equipment. But yeah, it's really in 1849 and going into late 1800s that we established, both in the U.S. and across the other parts of the industrialized world, a network for observing primarily temperature, humidity, barometric pressure, precipitation, all at the same time. So 1851, we have the first weather service established in the world in Austria. The U.S. As often as we have been first on things, we were definitely not the first in terms of establishing kind of a government-run service for tracking and understanding the atmospheric conditions at any given time. So now things start happening real fast in the science. You notice like a lot of things, and sciences in particular, you wind up spending all of this time, all of these eons, just coming up with the equipment to measure your science, your physical nature behind you. And once you've got those key measurements, and you can take those key measurements easily and rapidly, then the science advances really quickly. And that's kind of the phase that we started getting into in about the 1850s to the end, well, to present day, really. So 1854, UK starts their meteorological office. 1860, we get our first daily weather forecast. So even back then, the United Kingdom was trying to not just take in the data, but to try to make forecasts based upon the data that they were able to gather. So, I mean, if you're mentally doing the math, that's really only 140 years ago that we started actually trying to forecast the weather. So relatively speaking, when we're looking back 2,000 years, and it's only the last 140 that we've even started trying to forecast the weather, it puts a lot of this into perspective as to how young the science of meteorology actually is. 1880, modern global weather recording begins, and this is why you look at the National Weather Service. If you're breaking a major record that goes all the way back to the start of time, basically, you're never going to see a record broken prior to about 1880 anywhere in the world, because the records weren't kept any further back. So when we hear about, oh my gosh, new all-time record high temperature, it's not necessarily truly all-time record high temperature. It's an all-time record high temperature in about the last 140 years, which still is significant, don't get me wrong. But it is important to kind of keep some of that context and realize that over the span of human history, it's not really a record since the dawn of time. It's a record in the last 140 years when you hear records broken. 1881, Finnish meteorological office is formed, and then 1883, Tokyo, and then finally in 1890, the United States Weather Bureau, which is now the National Weather Service, is established. So again, that's only this year's 130 years of the National Weather Service, which, put that into perspective, National Weather Service only existed for 5 years before Wichita State University was founded, or Fairmount College, that is. So that does not go back that far. 1904, Vihelm Bjerknes says that it should be possible to forecast the weather from numerical calculations. This is a huge deal because before then, we weren't using necessarily math to make our forecasts. We were using observations. We were saying, okay, well, I mean, this is where you kind of get in some of your old wives' tales, as they say. You know, red sky at morning, sailor take warning. Red sky at night, sailor delight, is one of those type of just kind of sayings in meteorology. So a lot of forecasting before this time was just based upon, okay, the sky looks like this, so that's going to happen in about 12 hours. This is the first attempt to say, hey, wait a minute, we can apply some, mathematics, some calculations, some formulas to this to actually calculate what's going to happen when. And a lot of our understanding of numerical modeling and weather forecasting really kind of developed out of this. This is a huge thing between both Vihelm and Richardson a little bit later in 1922. He kind of takes that research and develops it further. The idea that was being applied that if we take enough observations at the surface and then through the atmosphere and figure out what the conditions are, temperature, humidity, barometric pressure, and dew point, well, no, that's humidity. If we take those measurements enough locations throughout the atmosphere, we can narrow things down and understand what's happening now and what's going to happen 12 hours from now, 24 hours from now, and so on. And then we get to March 25th, 1948. I'm pretty close to the right time. And we get a really big day in the advance of meteorology and atmospheric science. And that pulls me to my intermission point. So we're about 8 minutes ahead of schedule. We will still kind of go with a 10-minute break, but before we break, I'd like to open it up for some additional questions. We've about 8 minutes ahead of time, so I'm doing pretty good time-wise. If there are no questions, we're going to take 10 minutes, guys. Please try to be back on time for the people who are watching online, and we'll find out what happened on that fateful day, and we'll continue on. I remember I'm on camera now too. All right, everyone, welcome back. We do have a few questions that have come in. I'm going to answer the two questions, or see what I got here, via email, and then I have at least one question here in the room. And fortunately, I've got a little bit of time. I'm doing good time wise, so I think we'll be able to answer plenty of questions as they come in. First question is from Frederick, asking regarding measuring barometric pressure, the baseline to which all locations are calibrated as the pressure at sea level. Perhaps a stupid question. There's no stupid questions. But is this the barometric pressure on a stable day or a stormy day, since the pressure will presumably vary considerably at sea level depending on whether it is stormy or not? What is the weather condition assumed in the sea level barometric pressure baseline? Okay, not a stupid question. Basically, how we get to that sea level average barometric pressure is it's the kind of determined average pressure of the extremes. Just like with our average temperature, average, high temperature, average low temperature. Whenever you hear somebody say an average this, it's really kind of the average of all the extremes, all the data points put together. So weather-wise, it wouldn't necessarily be a stormy day or a clear day. It would be kind of somewhere in between, because that somewhere in between weather-wise would be kind of your average. If I had a weather map up, I could kind of point out on that weather map where your sort of average temperature would want, or average barometric pressure rather, would wind up being on the map, because it would be the location kind of in the middle of where you see your H's and your L's on a weather map. Because you're not really to the high pressure, you're not really to the low pressure. You're sort of in the middle of those two pressure extremes. So that's sort of where we get to our average barometric pressure. So hopefully that kind of answers that. Another question here. What does the measurement of air pressure indicate? It's a good question too, because I have a little extra time because I raced through some of that timeline a little faster than I should have. Basically what we are measuring when we're measuring air pressure is the weight of the air on a specific column of air. So we can think of, and I had this conversation during the break a little bit about comparing the atmosphere that we have around us to water. If you've got like a tank of water and you put a divider in the middle of the tank and you color half the tank red, with red food coloring, half the tank with blue food coloring, and the red side is hot water, the blue side's cold water, and you pull out the divider, you're going to see the hot water kind of gyrate around the cold water. You'll see these what are called eddies form, kind of little spirals in the water as it kind of mixes back together. And the atmosphere operates in very much the same way. Well, that hot water has a different density than the cold water. So if you're in the cold water side, that water is kind of in a very small way in this experiment, but it's slightly heavier than the warm water is. And the atmosphere is the same way. Warm air, as a general rule, is going to be less dense than cold air. And because it's less dense, it's not pushing down on the earth as hard as it is during if you're in a column of cold air, because the column of cold air is just, it's pushing down, it's tight together. And so that basically you can think of the measurement of barometric pressure, sort of like standing on a scale. That's the weight of the atmosphere on a specific point. So hopefully that helped with that question. Had another question I know over here. I can't remember what it was though. So, oh yeah, the Farmer's Almanac. Yes. Farmer's Almanac, I believe, goes back to I believe about the same time, maybe even a little bit before the formation of the National Weather Service. I believe it's late. I can't remember when they first published, but yeah, I mean, that used to, for a long time, kind of be a general reference point, not a terribly accurate reference point, but a reference point for long-term weather forecasting. If you've ever looked at the Farmer's Almanac and what they'll do is they kind of break up the weather sort of by region of the country that you're in. And then they typically will do it in a few days to a week span of time over a long period of time over, really the course of the year. Cooler, rainier, very general sort of forecasts. But over time, a Farmer's Almanac has been maybe about 50% accurate. It's the work that goes into it is taking a look at where the atmosphere is at a specific point in time when they're generating this forecast, and just propagating all of the systems over the course of a long period of time, and hopefully getting kind of close. But it generally is pretty inaccurate and very general in terms of forecasting. If you've ever looked at it, when it feels right, it feels like it's real right. But getting beyond the basics, the Farmer's Almanac could never really get into that. That being said, though, our longer term forecasts, because we do seasonal forecasts, the National Weather Service does, a lot of general long-term forecasting. And that, is similarly looking at, okay, what's the long range pattern at this particular point in time? And what do we expect? How do we expect those global patterns to move over time? And again, we'll get a little bit more into that next week when we talk about Rossby waves. Those are the really long wave patterns that go across the globe, both in the northern hemisphere and the southern hemisphere, that help us have an understanding of the long range or the long wave conditions that help drive the weather patterns. So, and that gets. We could probably talk several weeks just about that. So yeah, that we've come a long ways from the Farmer's Almanac, but Farmer's Almanac still published to this day, and some people swear by it. So yeah. So anyway, without further ado, I left you hanging here on March 25th, 1948, which was a very big, significant day in meteorology. It was on this date that the first tornado warning was issued. That's not that long ago. And, it was issued by a couple of Captain Robert Miller and Major Ernest Fawbush of the U.S. Air Force in Oklahoma. I can't blanking on what base they were on. Anybody remember what base is right near Oklahoma City? Tinker, yeah, of course. I don't know why my brain farted at that moment, but yeah, they were at Tinker. And there was severe weather approaching the area that they were seeing on the first generation radar screen. And they went ahead and issued a tornado warning, which was, in fact, a very big deal at the time because, believe it or not, issuing tornado warnings was banned by the U.S. government until 1950. They finally lifted that ban. By today's standards, that seems absolutely insane that you would not warn the public when there was a chance that they would be impacted by something as significant as a tornado. The government, though, was very paranoid that warning people would lead to chaos and panic and everything like that. And so it was banned to warn the public of something that might save their lives. And even after this tornado warning was issued and did save lives, the Federal Communications Commission ban on public communication of tornado warnings continued even beyond that. It wasn't until there was some additional pushback by, again, Oklahoma, the dead center of Tornado Alley, broadcast meteorologist Harry Volkman violated that FCC warning or the FCC ban rather, and alerted the public of another tornadic situation. He also was credited with saving many, many lives because there was a tornado on the ground. It did destroy a lot of things, but people did take cover and it saved lives. And it was through these acts of defiance that started to erode that ban on communicating severe weather to the public and making sure that we're doing what we can as meteorologists to keep people safe. As an aside, if you talk to most meteorologists and you ask them, why'd you get into the field? You get a lot of them will be very passionate about the fact that, we're in this not because we like getting on camera and making forecasts that people think are just wrong all the time. It's because, those rare times where there is very significant severe weather, chance for loss of life, that we have the chance and the opportunity to warn people and get them the information they need to be safe. It's just like your firefighters run into the burning building when everybody is running out of it. Meteorologists are on duty away from their families when the weather is at its worst, to warn people and keep them safe. So that's what draws a lot of meteorologists into the field, is the fact that you really do have a chance to make a difference in a family's life, in the public's lives. Buildings can be replaced, people cannot be replaced. And, that's the passion that went into those acts of defiance in issuing tornado warnings, which have saved thousands and thousands and thousands of lives. So we move into the 1950s. And the 1950s brought us some of our earliest computers. Remember, we talked before the break about Richardson, talking about if we take enough data and we run enough equations, we can forecast the weather accurately. Well, of course, in the early part of the 20th century, we did not have computers, and hand cranking all of these very long, ugly looking equations was just never going to happen in the time scale needed to get a forecast to the public before the weather already happened. And even today, we have massive supercomputers. Some of the most powerful computers in the world are here in the U.S., run by the National Weather Service, cranking out numerical models. And even those supercomputers that are cranking the models that we use operationally still take typically about 3.5 to 4.5 hours running in order to generate one set of numerical forecasts for meteorologists to use in order to guide their weather forecasts. But 1950s was where we were able to actually get things started and utilize some of the early computers to crunch those equations that Richardson came up with in order to add a little bit more sophistication, a little bit more consistency to how we're forecasting the weather. 1953, we have our first designation of what is, I mean, it had been observed, of course, before now, but hadn't really been named until Don Saggs at Illinois State kind of looked at and noticed that most of the time when you see a tornado on the ground, it's associated with this comma-shaped hook on radar. And you got to remember, we're still talking back in 1953, and in 53, we're still using radar from World War I and II. And so it's just that monochrome screen. You're not seeing any graduations in terms of color intensity. We don't have the color radars or anything like that. But we are noticing this hook shape, and that tornadoes tend to form underneath the hook shape. Yeah, I'll come back to that later. I was going to go off on another tangent. I like chasing squirrels, but I wasn't going to chase that squirrel. Moving on to 1959 or 57 rather, we finally get this first sort of advance of radars being deployed more nationally, and the World War II radars that were used were basically sent out to all these weather service offices for trying to observe the weather instead of being used in the combat situations that they had been used in. April 1st, 1960 is a big day for us. We're already well into the space race. And we have our first satellite image of the weather that we've been able to take. The Tiros 1 satellite was our first weather designated satellite, and it was launched. And that's those are the first pictures that we had from space of our atmosphere. We kind of take that for granted a little bit today. We can, we've got NASA astronauts up in space all the time, and we can get pictures from all sorts of our satellites, which we'll talk about in a second here. But that, again, 1960, we're in 2020. I was just 80 years, or I'm sorry, not even 80 years ago. I was 60 years ago. So not very long. And this is just giving us our photograph. It's not even doing some of the things that our satellites do for us today. So also in the 1960s, we have the development of this idea of chaos theory. The fact that no matter how well we think we can come up with our equations for forecasting the weather, they will never be perfect. We will never be able to capture every little thing that can impact the weather as it occurs. And so because of that, we need to have this piece on the end of our calculations, so to speak, that accounts for this chaotic nature of what we don't know. what we can't measure yet. Because as much as we can measure, even today in 2020, there are still things primarily on the micro scale that we're really not able to measure. We can get a lot of our data remotely from satellites these days, but that's not as accurate, and our satellites can't shoot through clouds, so we're still, even today, not able to measure every single place and every single detail on Earth. And what we can't measure is that chaos. And this concept of chaos, and this concept that there could be slight changes from what we're able to calculate to what happens in reality, leads to the spaghetti plots, the ensemble forecasts, as they're also called. And we see those most commonly during hurricane season. If you've ever looked at a hurricane forecast map, you'll usually see about half a dozen or so possible paths that the hurricanes could take. And we utilize those ensemble forecasts to create the cone that you see of, this is probably our 90% confidence cone of it's going to, the hurricane, we don't know exactly where it's going to hit, but we know it's going to hit somewhere in this area. And then May 17th, 1974, is the launch of the first GOES satellite. And GOES is a geosynchronous, I can't remember what the OES, well, the S is satellite, environment is E, geosynchronous observational environmental satellite. And these are put into the atmosphere. Geosynchronous means it stays in one place. We do have satellites that also are they rotate north to south around the poles, taking satellite images as well, and that gets us kind of a more global picture. But the GOES satellites are what here in the U.S. Meteorologists use primarily when they're looking at their satellite imagery. There are 2 GOES satellites in orbit operationally at any given time. And then typically there are 2 additional satellites that are not in operation but available in case a satellite goes down, which they do occasionally do. And they only last so long. And even if we could get them to last longer, the reason why we continue to launch up new GOES satellites is because our technology gets better by the year, it seems, and with each generation that goes up, we're able to do even more what's called remote sensing of conditions in the atmosphere and on the surface of the Earth. And so our last launch, which was the latest GOES West satellite, was launched March 1st of 2018, and that was GOES 17 we're on now. The next launch I looked appears to be planned for 2021. I can't remember what, I think it was August, but I'd have to go back and double check. But yeah, that'll be designated once it's up there, and operational will be designated as GOES 18, which I believe will, it would be replacing GOES East. So you got one satellite that kind of takes pictures of the western half of the U.S., one that takes pictures of the eastern half of the U.S., and at this point, they're very high resolution photographs at this point. Going back to our GOES 1 satellites and some of those early government satellites, back then, the best we could do was about a half-mile resolution. Now that resolution is, we're talking in the feet with some of these new GOES satellites. It's very, very detailed imagery now. Any questions? 1975, I'm almost born. Color weather radar is developed by the National Severe Storms Laboratory. They're down in Norman, Oklahoma. And this gives us the opportunity to now kind of get a better visual, not just for the meteorologists, but also for the public, a better visual feel for the intensity of storms. Before this time, we weren't really able to visualize storm intensity real well. But after 1975, with this advent of colorizing from light green all the way to basically purple, it's the scale that we use to this day. Light green would be light rain. Reds are intense, heavy rain. And if you get into those purples and pinks, if you see those on the radar, that's usually going to be a hail, a column of hail falling. 1981 to 84, National Severe Storms Laboratory attempts to deploy TOTO, the Totable Tornado Observatory. For those of you who have seen Twister, yes, this is kind of sort of loosely what Twister was based on, this concept. Basically, they would, the NSSL is at OU. And so what they would do is the professors would go out storm chasing with their graduate students and send the grad students out to put this about yay big instrument thing that I think weighed, I want to say it weighed about 100, 150 pounds. So I had to carry this thing out in front of a tornado, set it down, and then try to hightail it out of there. And that was their first attempts to try to get some observations in and really near tornadoes. And I don't know that they were ever successful when they did that, of actually having one sit in front of a tornado and get a tornado to go over top of it. But that was what they were doing back then. And 1988 to 2004 is when we get our modern radars that we use to this day. It was a big advance in the technology from what we had before, in the sense that earlier radars, the kind of Generation 1 radars, measured what's called reflectivity. Basically, what we do is we just send out a beam of energy. The beam of energy bounces off the clouds, bounces off of precipitation, bounces off birds in close proximity of the station, and then comes back. And based upon the intensity of the receiving of the reflected beam back to the station, measured the intensity of that actual storm or cloud or whatever. What NexRad did was it measured a second thing and measures a second thing, which is really critical for severe storm observations and forecasting. What NexRad measures as well is radial velocity. Radial velocity is the measurement of the wind coming toward and going away from a particular radar station. So if you've ever seen in a severe weather event, the meteorologist puts up a different looking screen from your reds and your yellows, and it's kind of greens and reds. And why that's important is because where you have winds rapidly moving away from a station and rapidly moving toward a station right next to one another is probably where you have a mesocyclone, or potentially, in an extreme case, a tornado at that location. So whenever you see that graphic come up, what the meteorologist is probably pointing out is where you have a dark green right next to a dark red pixel on the screen, and that's most likely where you're going to have your tornado warning at. Those pixels right next to one another is referred to as gate to gate. is something that you might hear meteorologists talk about, and they'll refer to a gate-to-gate of 100 miles per hour or whatever. It basically what they're doing is they're rattling off the difference from the one extreme to the next extreme at the pixels right next to one another. And so radial velocity allowed us to, on a radar, get a pretty accurate visual understanding of where a tornado is either on the ground or forming. Before this time, before the late 1980s, we really were just working off of reflectivity. We were still into the late 80s forecasting or warning really tornadoes based upon looking for those hook echoes. So, okay, real intense storm, high reflectivity, kind of a hook notch there. So we'll warn that as a tornado. Problem with doing that is there's a lot of little notches, a lot of, things that you would see in reflectivity that don't necessarily pinpoint where a tornado actually is. And by having the relative velocity, we were really able to pinpoint where a tornado is most likely on the ground. When this came out, it radically improved our ability to not only observe where tornadoes are, not only warn much further ahead of time of tornadoes, but it also helped us observe and understand a lot of other weather phenomenon. In particular, and this might be one of the things that is at least as positive, if not even more positive, with the advent of the radial velocity, is our ability to now observe downbursts, microbursts in the atmosphere. One thing that we have noticed over the last about 30 years is we don't have any, well, there are some, but it's rarely, if ever, weather related. You don't have aircraft crashing anymore. It used to be that you had a lot of weather related aircraft accidents because aircraft would be coming in to the airport or going out of the airport and would hit something called a microburst. Basically, a microburst is the air coming down in a column from the upper atmosphere, usually a collapsing thunderstorm, hits the ground and kind of spins up from that column of air. It creates a lot of turbulence in the very low atmosphere. Well, that was something that pilots couldn't see, air traffic control couldn't see. Nobody knew if something like that was there. And it used to, before we had this, lead to a lot of aircraft accidents. But since we've been able to observe these winds, we're also able to observe when there's a microburst happening, and we can keep aircraft away from flying through that area of high turbulence. And as such, it's estimated that tens of thousands of lives have been saved over the last 30 years just based upon not having these crashes that are weather related. In fact, I think it's been 15, 20 years since the last true weather-related major airline crash. You still get some of those as they relate to private aircraft. But in terms of our major airlines, we know enough now that we're able to steer aircraft clear of any potential low atmospheric turbulence. Okay, not all meteorologists are on TV. Most are not. I was not. As I mentioned early on, I worked with Mike Smith at what is now AccuWeather Enterprise Solutions. I worked in the newspaper and utility division. So I did forecasting for newspapers all across the country. I also would forecast for various utility clients. Most notable, the largest client that I did on that side was Southern California Edison. We had to do an hourly forecast for them going out 10 days. And the reason for that, I mean, is simply because one of the things that utilities do, and I didn't realize this when I got into forecasting, but what they do is the big business is energy trading. So one company will make a certain amount of energy, generate the energy, and then sell that energy off to another company. And if you've got really accurate forecasts, well, that means you have a good feeling for what that energy demand is going to be a week or 10 days from now, and you can generate the right amount of energy today, not just for your customers, but also for another company's customers. And so there's a lot of that energy trading back and forth that takes place. So yeah, we did hourly forecasts out 10 days for them. Once you get past about 3 days, it's kind of pretty generalized. But you know, you're always trying to catch those trends as a forecaster when you're forecasting for a utility client out far enough that they can take that data from you and operate their equipment in a manner that is most profitable for them. So areas of meteorology, some of these are kind of straightforward, some are less straightforward, but these are all kind of the major areas. As I kind of mentioned, I worked in straight up forecasting. In my case, I wasn't doing public forecasting. Commercial meteorology is primarily a business to business type of transaction. In this kind of day and age, it's oftentimes kind of a part of your business risk management. These days, AccuWeather not only is doing forecasting per se, but working with large corporations to help with their weather risk management, and also helping with decisions as to and this is particularly in retail, decisions in terms of how to take advantage of different weather conditions. If you've ever noticed when you go to a Target or a Walmart, you walk in the day before a major weather event or whatever, and you see umbrellas and other things out, or if it's right ahead of a ice storm, you've got all sorts of calcium chloride bags sitting out so that you can salt your sidewalks. Weather data works, AccuWeather works with some of these major retailers to provide them with some of that information on, you might want to buy extra of this and push this product to your consumers to increase your sales. So, that's kind of an area of meteorology that we as public consumers, just watching the meteorologists on TV, we don't really think about. But in terms of business, having a good feel for not only your business risks from severe weather, but also utilizing weather data in terms of being proactive in some of your decision making for your business. That's a lot of what AccuWeather did back then and does even more so today. Aviation meteorology is specific to understanding the weather conditions in terms of how it's going to affect aircraft. A lot of work in this area is done in terms of trying to steer planes away from areas of high turbulence in the middle and upper atmospheres. Agricultural meteorology, that's a big area, especially in this part of the country. Your ag forecasts in terms of weather are attempting to assist farmers in terms of, how much do I have to water this crop, everything like that. Harvest. The list goes on and on in terms of the applications to farming. Hydrometeorology is specific to lakes, rivers, bodies of water, everything from tidal forecasts to wave, sea heights. I originally grew up in Western Michigan, and so the hydrological forecasts were a big thing up there in terms of forecasting what the wave heights would be for marine travel and that sort of thing over the Great Lakes. This one seems a little bit stranger. Nuclear meteorology. This is the science and the study of radioactive particles in the upper atmosphere and how they move around. Maritime meteorology kind of goes along with hydrometeorology a little bit. Military employs a lot of meteorologists, especially in the Air Force. If I hadn't met my, at that time, future wife when I did, there's a pretty good chance I would have wound up in the Air Force. A lot of good jobs there for meteorologists, doing everything from general forecasting to if you're in a active theater of war and you're flying a plane, probably a good idea not to have your plane kicking out contrails. And so meteorologists in the field would give and do give forecasts to aircraft pilots saying, if you're flying in these levels, you're going to be producing contrails versus other layers where you won't be. Some people will talk about contrails in terms of chemtrails, that the government is spraying chemicals on us. I assure you that is a joke. We know based upon the type of engines that are produced and the output from those engines, based upon the humidity levels in certain parts of the atmosphere. It's complicated because it goes by the actual engine, but if the type of engine that's flying through a type of a specific layer of the atmosphere, temperature and humidity, you're likely to produce a contrail behind your aircraft. So you'll notice if you look up, some days you'll see from commercial aircraft all sorts of contrails going across the sky versus other days where you won't see anything. Again, it's about the conditions at that layer of the atmosphere, usually 25 to 35,000 feet, where they're at cruising altitude. When you've got all these contrails being produced, the conditions are favorable to the production of contrails behind the jet airliners. Environmental meteorology, that gets into climate change, things like that. That all falls under that header. And then medical meteorology, kind of go into the question that I had earlier. That's the area of primarily research, where they're researching how the weather impacts kind of how we feel and how we kind of act. And then finally, renewable energy utility meteorology. That's a little bit, at least a sliver of that is what I was talking about before, where I'm doing where I used to do forecasting for utility clients so that they can make decisions on energy production, and then the renewable energy component relates to like, for example, with your solar panels, how much energy am I going to produce on a specific day based upon how much sunlight I'm going to get at a location. That's kind of gets into that. And I am still ahead of time. That's good. I've got plenty of time for some questions. These are some. These are basically the apps that I have on my phone that I like to use when I'm kind of looking up forecasts and also looking at radar. There are dozens of apps out there. Some may even be better than what I have. I've these are the ones I like and I use all the time. AccuWeather's one of them. I use that for point specific forecasts and guidance. And then Zoom Weather is, as opposed to Zoom, the video conferencing, it's a little bit confusing now. Zoom used to be called WeatherTap, and back when I worked as a meteorologist for weather data back then, even at a commercial level, this was what we would refer to for weather radar. Along with the National Weather Service, we'd look at both. And it's a very good radar app. If you don't have it, you can zoom in real tight. And it also has track lines for something that is, I believe it's free, and then you can upgrade it to a pro version. But even the free version is really good in terms of monitoring the radar. Only problem with Zoom is it's unfortunately only on iOS, at least the last I looked. But that's a good one to go to as well. I see some people. If you want to look at this later, I'll pull this back up. These are some, and unfortunately up here, it put the it's the links are clicked and are showing up clicked and in blue here. But this first one is National Weather Service Wichita page. If you've never been there, it's just www.weather.gov ICT. ICT being the three-letter identifier for Wichita. The next one is the Storm Prediction Center, Convective Outlooks. I frequently look at these when we're in storm season. They're the ones that produce the day 1, day 2, day 3, and then now they do days 4 through 8, which I don't even know why they really do that, because it's that product is, in my opinion, not that useful. And they kind of show the hashed areas of where the Severe Storm Center thinks is the highest likelihood for tornadoes, thunderstorms, hail, that sort of thing. And you can get to that www.spc.noaa.gov/products and /outlook. Another one that I look at here, and I think most of you guys have the slides available to you, if not all of you. So these are all on the slides as well. Wonderground.us is that one. I might as well click on a couple of these. Actually, maybe I shouldn't have clicked on the link. Well, actually, that made it look like a little better. Yeah, I won't jump back and forth because I don't want to mess things up for showing the. Can I go back and forth on this and be okay? Okay, we'll take a look at least here. Maybe. This is another site where you can get take a look at some weather maps, things like that. We back in the day, at least, go to the Wonderground as well for taking a look at some. Oh well, actually, my site there has changed. I'm going to have to take a look at that. Weather.us is another good one. Obviously, I haven't been to Weather Underground for a while. Well, this is going really slow. Try to at least pull up a couple of these since I've got a little bit of time here. National Hurricane Center. That one's a little more timely for this time of the year. Come on. There we go. Okay, so we've got a little bit up here. Weather.us. So you search your weather forecasts. Heck, they even have stuff on COVID-19 up there right now. Okay, well, this is going real slow, so we can maybe look at this later as well. Oh, there we go. So you can get the hurricane tracks and everything like that on here for the National Hurricane Center. And yeah, there we go. So you see Isaias on landfall in New Jersey. And right here looks like a chance for another tropical disturbance here coming up. Okay. So a lot of good information, a lot of products down here, wind speeds, probabilities. So if you want to nerd out on some weather stuff, there's plenty of sites that you can do that on. Okay. Oh, yep. So, all right. Just about set there. Okay. So next week, as I alluded to at the start of the class, we're going to kind of get it a little bit into the day in the life of a meteorologist. So I'm going to kind of walk you through back when I was actively forecasting as an operational meteorologist, what I would do during my day. And then we'll learn a little bit about severe weather spotting, chasing. Is it like it is in the movie Twister? I assure you it is not. And weather forecasting, or severe weather forecasting as well. And with that, we got a little bit of time here. Be happy to take some questions. It looks like I've got some from those of you online. Thank you for those. And so I'm going to read these quick while you guys are trying to think of any questions that you might have here in our on-site audience. And for those of you out there still, if you want to send some more emails through, I've got 14 minutes for it. So I time my second half here out pretty good, so that we had plenty of time. Okay, Calvin asks, this may be covered before the class is over today. What is the difference between a cyclone and a tornado? I did not cover that. A cyclone, well, a cyclone in general is just a kind of a synoptic scale circulation. Now, synoptic scale is anything from about 100 miles, about 100 miles across to about 200 to 300 miles across. It's basically a large scale circulation over an area. Cyclonic circulation could be anything from a low pressure system moving across the U.S. to like a hurricane moving across the Atlantic. Those are cyclones or cyclonic circulations. A tornado would be what we would call kind of a mesoscale circulation, a very small scale. With tornado, you're talking meters to maybe a mile or so in terms of circulation. So they're both circulations. It's just the scale of those circulations is different. Thank you for that question, Calvin. And I've got another one here from Frederick. Where do you see meteorology continuing to advance in the coming years? I'm thinking of things such as new technology under development and what will it yield. What areas are getting the most research, focus, attention, and what is the targeted improvement? Well, really, the targeted improvement, I can attack that one. It's continuing primarily to advance both our understanding of kind of on a global sense, the atmospheric conditions and the changes in those conditions with time on the one end. So on the macro scale, it's that looking at climate and how it's changing with time and that sort of thing. On the totally flip side of that, on the micro scale, it's getting more sophisticated and better information that we can improve our severe weather forecasting, especially as it relates to tornadoes, and getting more increased lead time on tornadic development. As far as technology, the big thing is just continuing to increase the performance of our numerical models, which means that, from a technology standpoint, getting computers that are able to operate faster and faster and faster, because if we get the computing power faster, that means that we can put more data into our numerical forecasts. And the more data we have, in theory, as long as the data is good, we're going to get better forecasts. If the data is bad, then it's like the, thing that you say, garbage in, garbage out. So our numerical forecasts are only as good as the amount of data and how good the data is going into it. As far as radar technology, we currently are in NEXRAD, which has been deployed now, fully deployed for about 16 years. That will eventually be replaced, or at least this is the talk right now, by LiDAR, which is a laser form of radar. And LiDAR, one of the advantages of utilizing LiDAR over radar is it's basically instantaneous. At that point, the ability to have radar images much closer to real time is possible. When you look at a weather radar image currently, and this is the way it's been for the last 20, 30 years here, that image is roughly 3 to 5 minutes old by the time you view it. It takes about that long for the radar to fully loop and process all of the different angles that it's taken a shot of as it goes around a specific station. That takes a while, which, when you think about, a general situation, maybe that's not that big of a deal, 3 to 5 minutes. But if you are about 3 miles away from an oncoming tornado, 3 to 5 minutes is a pretty big deal. And so through hopefully better development of LiDAR technology, once it gets to a stage where it can be utilized at weather service offices, that's going to be a pretty big advance in radar technology. Timeline on that, last I heard, it's still a long ways out because LiDAR is pretty darn expensive. But LiDAR is also being utilized in autonomous cars, and so its use is increasing fairly dramatically. And so my guesstimate would be, as that technology gets used more and more, like a lot of technology, it will start to become cheaper and cheaper, and hopefully a little easier for the weather service to use. The LiDARs that are on your cars that are coming out for autonomous driving, those ones are, they're expensive as it is, but they're only shooting a small space right around that car. The Weather Service needs LiDAR that can shoot out 50 to 100 miles from a station. That requires incredible power, and with incredible power comes a lot of expense. So those are some of the things that I see in the near term. Okay, yeah, those were the 2 questions that have come in via email. Are there any questions out here? Yes. Mm-hmm. The question was regarding wind farms, and do wind farms have an impact on the weather around them? That's actually an area that is being actively researched and has been actively researched as wind farms have started to pop up. Given the fact that these really large scale wind farms, like for example, you see what some of it going down 35 South, and huge wind farm out in western Kansas as you drive down 70 out toward Colorado. That's still an area of very active research as to whether or not that is having some impact in the near surface conditions. I don't think it's something that we really know necessarily how much of an impact it has yet, but it is something that is being actively studied. Good question. Yeah.
I've noticed sometimes that the wind turbines are operating.
Mm-hmm.
Some of them are, some of them aren't. Sometimes I drive by and none of them are. Sometimes I
Mm-hmm.
drive by and all of them are. Is that due, and I know we sell a lot of that energy to the East
Mm-hmm.
Coast. Is that due to those being turned off and on?
The question was related to wind turbines in terms of sometimes they're all on, sometimes some of them are on, sometimes they're all off. And is a question about why that is. Okay. I know some of it would be just simply, is there enough wind energy to be captured? That's, I know a part of it. I don't know exactly what leads to all of those decisions being made in terms of why they're on, why they're off, because that's kind of been something that I've wondered myself. And so I'm honestly not sure. I mean, obviously those wind turbines expend energy as they take it in. And so I have no doubt that there's some sort of calculation of, okay, hopefully I am capturing more energy than I am expending. Otherwise, why am I running this turbine? So that would be my best guess, but honestly, I'm not exactly sure what that decision making would be.
Well, I can see where the weather forecast
Mm-hmm.
would be helpful to those in control.
Oh yeah, I can guarantee that the utility companies, whether it be Evergy here locally or wherever else you go in the country, they definitely, if they don't have meteorologists on staff at those companies, they would be going, and frankly, a lot of them do already go to either AccuWeather here in Wichita or some of the other commercial weather firms across the U.S. Fun fact, with the railroads in North America, the track warnings that are issued for, and a track warning is issued for a span of track that a train would go across based upon certain criteria, like the obvious would be a tornado going across the track. We need to warn that mileage of track and stop any trains from going through there. But something that you wouldn't think about, that that is warned for spaces of track, is when when the temperature's above 90 degrees. When the temperature gets above 90 degrees, the actual ties, the track itself can start to buckle, since it's metallic, it's metal, And so as the track warms, it tends to buckle. And so when there's a temperature gets up, it gets worn, and somebody's got to go out and make sure that the track isn't buckling, because that can lead to a derailment. Anyway, bringing that back around, all of those warnings, private warnings for the tracks across the U.S., whether it be Union Pacific track or Burlington Northern track and some of the others across the U.S., all of those track warnings come out of Wichita. They're all generated by AccuWeather downtown. That's one of the major clients for AccuWeather right now. Yes.
I've heard meteorologists say that technology is wonderful, eyes on the ground, and tremendous help.
Mhm.
I'm wondering if too many amateurs are interfering with legitimate storm chasers.
The question was related to storm chasing and the fact that having eyes on the ground, also kind of called ground truth, is a big support to meteorologists who are trying to warn people of severe weather, tornadoes, that sort of thing. But is the on the flip side, is it a benefit or not a benefit for amateurs to be out there also chasing storms and that sort of thing? And it's a mix. Historically, we didn't have all sorts of amateur storm chasers out racing around like we do today. A lot of that kind of started developing as as photography improved and as video camera technology improved. Before that, it was primarily just law enforcement and amateur weather enthusiasts who were volunteers with the National Weather Service who would go out in severe weather to do that ground truth observation. Nowadays, you get a lot of people just jumping in the car. Hey, let's go chase storms. And I have heard, now I am not an active storm chaser myself. I did a little bit during college with our university department storm chase group. But I haven't gone out storm chasing in a couple decades now. But what I have heard from people that I do know that go out chasing is that one of the big problems is that there are a lot of people on the roads. There are a lot of chasers out there, and it leads to kind of traffic jams as all of these chasers are trying to go to specific locations. And trying to get the best shots and everything like that of the storms. And that does lead to the potential that somebody's going to get stuck in the way of severe weather and get killed. It amazes me at this stage that we have not had more deaths of chasers. Really, there's only been a few notable chasers that have been killed in a tornado, and we'll get into that next week. But it is a potential problem on the roads these days. The ground truth is good, and we're getting a lot of good information from that. But yeah, there's a real chance that because there's a lot of chasers out there, that somebody's going to get hurt. Yes.
All the positions of meteorology that you could go into, what does it take to get to the television? And was that something you ever wanted to do?
Oh, I've got a face for behind the scenes. No, I never really pursued or wanted to get into broadcast, mainly because I knew just, from meteorologists I knew growing up who were, in broadcast, that it's a very volatile field. You're having to uproot yourself and your family, you oftentimes every couple of years to go to a new city. And, that was kind of how you advance through the field, is start in a really tiny market and, prove yourself there, move to the next bigger market, and the next bigger market, and the next bigger market. And that, that's how you make more money in that field. And for me, it was not the kind of environment that I wanted to put myself or my family in. Because, you at that point you become a celebrity, and you go out and people, hey, what's the weather going to be like, and things like that. And that was just not the kind of life I wanted to live. Now, do I know people in the field who are on TV? Absolutely. I don't really know the ones local right now very well, although what's her face? I'm blanking on her name. Head meteorologist at KSN right now. Yeah, Lisa. I've not met her, but her and I both had some of the same instructors, albeit at different universities. She graduated from University of Georgia, and I graduated from University, Valparaiso University. And we both had Dr. John Knox as a professor who was awesome. And he's so, I mean, I also know had similar tracks with Ginger Z, who's now on Good Morning America. I never met, I probably met or crossed paths with Ginger at Valparaiso University. She was a freshman when I was a senior. So at that point, we weren't anywhere nearly in the same classes, but she was another Valpo grad and wound up going into TV. There's a handful of others that was kind of what they wanted to do. My minor was in broadcast communication, so I did do some of that, but it was more because I thought it was kind of fun rather than, wanting to really do it as a career. I was just happy, having my desk, my maps in front of me, and have the stability of knowing that I wasn't going to have a new owner, a new producer come in the next week and can the entire staff and bring in their own people, which does happen in that industry frequently. Other questions? Okay, well, I'll stick around for a few more minutes before I take off, if anybody has any last thoughts or questions. Otherwise, I'll see you next week. I know that the room is going to be different. I don't know. I can't remember the room number offhand, but I'm sure you'll get directed in the information that you need on that. And we'll be talking weather forecasting and severe weather next week. Thanks a lot, everyone. Mm-hmm.